Hi, welcome back to Physics Form 4 SSM. So we continue Chapter 4 Heat on topic 4.2, Understanding Specific Heat Capacity. Let's get started. Okay, look at this situation. The sun heats up the sand and the seawater at the same period of time. However, sand gets hot quickly and the seawater gets hot slowly. That's the boy saying that the sand is hot. And this one, the seawater is cold. So how can you explain this situation? So under this topic, we are going to explain what exactly happened and the concept involved, that is heat capacity. Okay, now look at the idea of heat capacity. A pail of water from a swimming pool has been left for several hours beside the pool. At noon, a lifeguard puts one hand in the water of the swimming pool and then into the pail. He found that the water in the pail is hotter than the water in the swimming pool. So what does he infer from this observation? So the inference is a body with a larger mass requires more heat to raise its temperature by 1 degree Celsius. In the case of the swimming pool, it contains a large amount of water, meaning larger mass of water. So it needs more heat to raise its temperature by 1 degree Celsius. So it heats up slower as compared to the water in the pail. The water in the pail has smaller mass, right? Okay, look at here. Different materials store different amount of heat energy. When we talk about different type of material, example gold and water. Say we have 1 kilogram of gold and 1 kilogram of water. So water takes about 30 times longer to heat than gold. So the gold heats up faster compared to water. So meaning different type of material store different amount of heat energy. Okay, look at this one. We have a kettle contains 1 liter of water and here is 2 liter of water. Let the water boil. We observe that the kettle with a small amount of water, that is 1 liter, the water will boil faster compared to 2 liter of water. The water in a full kettle takes a longer time to boil compared to the water in a half-filled kettle. This shows that water of bigger mass has a higher heat capacity compared to water of smaller mass, meaning it requires more heat energy in order to increase its temperature by 1 degree Celsius. Okay, what is the definition for heat capacity? So heat capacity, we use the symbol capital C. The heat capacity of a body is the amount of heat that must be supplied to the body to increase its temperature by 1 degree Celsius. So from the definition, we can write a formula for heat capacity. C equivalent to amount of heat. We use the symbol capital Q, or quantity of heat supplied. To increase temperature by 1 degree Celsius means per unit temperature. So that's why we have here C equivalent to Q divided by delta theta. Delta theta means change in the temperature. The symbol like a triangle here is a symbol for change or difference in temperature. So the unit for heat capacity, based on the formula here, quantity of heat is joule, delta theta is degree Celsius, then we can write C equivalent to joule degree Celsius to the power -1. The change in temperature also can be stated in Kelvin because the value change in temperature are same when you use Kelvin or degree Celsius. So meaning the unit that can be used for heat capacity is also joule Kelvin -1, same. Okay, now look at this one. We have material A, aluminium, A and B, aluminium, and C is plumbum. A, 2 kg of aluminium, B, 4 kg of aluminium, C, 4 kg of plumbum. Okay, look at here. 2 kg aluminium needs 1800 joule of heat to increase 1 degree Celsius in temperature. B, 4 kg aluminium needs 3600 joule of heat to increase 1 degree Celsius of temperature. And then for C, plumbum needs 520 joule of heat to increase 1 degree Celsius in temperature. Okay, for first part, let's look at A and B. For same material, aluminium, but different in mass. So as you can see here, based on the observation here, we can conclude that larger mass of aluminium requires more heat to increase temperature by 1 degree Celsius. So the larger the mass of the substance, the larger the heat capacity needed. So meaning this 4 kg requires more heat capacity compared to 2 kg aluminium. Okay, now you look at between B and C. Same mass, 4 kilogram, but different type of material. So you can see here, aluminium requires 3,600 joule of heat to increase 1 degree Celsius of temperature. But the plumbum for same mass needs only 520 joule of heat to increase 1 degree Celsius in temperature. So what we can conclude from this observation? So the 4 kilogram of plumbum requires less heat to increase temperature by 1 degree Celsius as compared to 4 kilogram of aluminium. So we can conclude that for same mass of material, the different type of material requires different heat capacity. So from this activity, what we can say about the factors that affect heat capacity? So we can say that the heat capacity of an object depends on mass of the object. An object with larger mass will have a larger heat capacity than object with smaller mass of same material. Second, type of material. Different material have different heat capacities. Okay, now there's a daily situation involving heat capacity. Look at this one, the first one. After being left to cool for some time, the soup in a large bowl is hotter compared to the same soup in a small bowl. Now we have discussed before that the heat capacity or amount of heat required to increase 1 degree Celsius of temperature depends on mass. So the large bowl of soup, okay, contains more heat capacity compared to the small bowl of soup. Second, at noon, there is a significant difference in temperature between cement cord and crust. So there are two different types of material, cord and crust. So they will have different heat capacity. Okay, so heat capacity also depends on type of material. Okay, the third one, why do the metal parts of the car get really hot while the plastic and other materials stay at more bearable temperature? Let's say you park your car under hot sun. Of course, the body of the car is very hot. Even you try to touch the body, it's very hot. But if you touch the part which is made of plastic, that one is more bearable temperature. It's not really hot, that part. So this one also explains that heat capacity depends on type of material. Okay. Okay, now we want to discuss what is specific heat capacity. We just add one word before heat capacity, so it becomes specific heat capacity. Now the symbol is small c. So what is definition for specific heat capacity? C of the substance, quantity of heat needed to raise the temperature of 1 kilogram mass of substance by 1 degree Celsius. Okay, did you detect the difference in definition between specific heat capacity and heat capacity? So for heat capacity, we have discussed earlier, is amount of heat required to increase temperature of substance by 1 degree Celsius. No mention about 1 kg mass. But for specific heat capacity, need to mention 1 kilogram of mass. Okay. Thus, the formula for specific heat capacity, we have small c equivalent to amount of heat required per unit mass per unit change in temperature. So we have C equivalent to Q divided by M delta theta. Okay, now look at what is the symbol means. For Q, heat supply or release, the unit is joule. M is mass of substance, unit kilogram. Delta theta is temperature difference. It can be temperature rise or decrease in temperature. The unit is degree Celsius. We can also use Kelvin because same value, temperature difference in Kelvin or temperature. Okay, the small c, specific heat capacity. So the unit for specific heat capacity is joule per kg per degree Celsius. So we get joule kg -1 or degree Celsius -1. 1. Or you can write also joule kg negative 1, Kelvin negative 1. Okay. Okay, now look at the exercise 1. What does it mean by specific heat capacity of aluminium is 900 joule per kg per degree Celsius? What does the value means? It means that 1 kg of aluminium requires 900 joule of heat to raise its temperature by 1 degree Celsius. Okay, so for each of 1 kg substance, the value of the specific heat capacity shows how many joules of energy required for 1 kg mass to increase temperature by 1 degree Celsius. Okay, now look at, we have B and C. B, 1 kilogram of aluminium. C is 1 kilogram of plumbum. For B, aluminium needs 900 joule of heat to increase 1 degree Celsius of temperature. Plumbum needs 130 joule of heat to increase 1 degree Celsius of temperature. So from here, because of B and C, the mass is 1 kilogram. Thus, we can make conclusion that specific heat capacity of aluminium is 900 joule kg negative 1 degree Celsius negative 1. And specific heat capacity of plumbum is 130 joule kg negative 1 degree Celsius negative 1. So what are the factors that affect specific heat capacity? So from here, we can say that specific heat capacity does not depend on mass, but depends on only type of material. So different type of material will have different specific heat capacity, and the value is already constant. Okay, so we can look at the relationship between heat capacity, capital C, and specific heat capacity of a substance, small c. Okay, we have discussed earlier heat capacity, capital C, equivalent to Q divided by delta theta. So this one you put as formula 1. Specific heat capacity, small c, equivalent to Q divided by M delta theta. So this one we mark as formula 2. Okay, now we want to relate between capital C and small c, heat capacity and specific heat capacity. From equation 2, we rearrange the formula. So C equals 1 over M bracket Q divided by delta theta. From 1, Q divided by delta theta is capital C, or heat capacity. So we substitute here. Thus we get heat capacity, capital C, equivalent to mass multiply specific heat capacity. So we have this formula. So this one relates between heat capacity and specific heat capacity. So from here we can say the specific heat capacity does not depend on mass. Heat capacity depends on mass. Okay, so amount of heat required also can be calculated from equation 2. So we have Q equivalent to MC delta theta. Or most of the book just write down Q equivalent to MC theta. So need to understand what is meant by theta. Theta is temperature difference or change in temperature. Okay, so this table shows the value of specific heat capacity for different type of material. So we have liquid, gas, metal, non-metal. So you can see here for liquid, normally liquid has very large specific heat capacity compared to metal or solid. Okay, so you can look at water, 4,200 joule per kg per degree Celsius, the highest value, okay, for liquid. So no need to memorize all the value. If there is a problem solving, they will give you the value. Okay, now, next we have an experiment for you all to determine specific heat capacity of water and determine specific heat capacity of aluminium. Okay, so you can refer to your textbook on page 129. Okay, so the first activity, you want to determine specific heat capacity of water. Apparatus and material, power supply, immersion heater, beaker, stopwatch, thermometer, retort stand, electronic balance, water and tissue paper. So look at the arrangement here. So we have a beaker, okay, you put some water inside and then put in immersion heater that connect to the power supply, and then a thermometer, okay, that hang from a retort stand. Okay, so cover the beaker with a tissue paper in order to prevent heat loss to surrounding. Okay, so when you turn on the switch, you need to record all the temperature reading of the water. So what we need to record in the table here, okay, you record what is a power of immersion heater, P, watt. So you can refer to the label. Most of the immersion heater, there will be a label. So power in watt. Heating time, what is the total time taken needed for the process? Mass of water, m kilograms, so you can weigh the mass. Initial temperature, record theta 1, okay? And then the final temperature after heating time that you have already set is theta 2. Okay, now from the table that we have record all the readings here, calculate the specific heat capacity of water using the formula C equivalent to Q divided by M delta theta. So in this case, the amount of heat supplied equivalent to power multiplied time of heating. So Q equals to PT. And change in temperature equivalent to final temperature minus initial temperature. So theta 2 minus theta 1. So we get the value of specific heat capacity of water by this activity. Okay, the second activity to determine specific heat capacity of aluminium. So apparatus material needed, power supply, immersion heater, 1 kilogram of aluminium block, stopwatch, thermometer and retort stand, tissue paper. Okay, but now we use aluminium block, 1 kg. The aluminium block has two holes here, one to insert the immersion heater and another one for thermometer. So you just put a drops of oil into the hole so that it will produce uniform heat transfer to the from the heater to the aluminium block and from the aluminium block to the thermometer. Okay, so you wrap the body of the aluminium with tissue paper to prevent heat loss to surrounding. Okay, so what we need to record in this activity, so you record power of immersion heater, heating time, how many seconds, mass of aluminium, here is 1 kilogram, so just write 1 kilogram, initial temperature, theta 1, and final temperature, theta 2, after the set time of heating. Okay, from the table, we can calculate the specific heat capacity of aluminium using the formula C equivalent to Q divided by M delta theta. Amount of heat required Q equals to PT, and delta theta is theta 2 minus theta 1. So we can calculate specific heat capacity of aluminium. So there are two activities for you all to determine specific heat capacity. Okay, now, due to the heat loss to surroundings, the value of specific heat capacity that determined from experiment is higher compared to the actual value. Why? Okay, we cannot get exactly the same as the actual value because our assumption is there is no heat loss to surrounding, meaning heat energy supplied by heater equivalent to heat absorbed by water. That cannot be because there's always heat loss to surrounding. When there is heat loss to surrounding, the final temperature cannot rise higher. So this one will cause change in temperature becomes smaller. So when change in temperature is smaller, from this relationship, we get higher specific heat capacity. That's the reason why the value determined from this experiment is larger than the actual value. So when you do this experiment, you get the value. So you just write a discussion explaining that there is heat loss to surrounding that causes the change in temperature to decrease. Thus, the value of C that we get is larger as compared to the actual value. Okay, now look at the application of specific heat capacity. Selection building material of traditional houses in various climate zones. Look at here, warm climate. Okay, like in Malaysia, warm climate and cold climate. Okay, for the warm climate, wood is used because wood has a high specific heat capacity and gets hot slowly. In warm weather regions, traditional houses are built from wood, which functions as an insulator of heat from the scorching sun. So meaning not really hot, very hot inside the house due to the wood that has high specific heat capacity. Okay, for the cold climate, in cold weather regions, traditional houses are also built from wood. Heat from fires lit in the wooden houses cannot flow out because wood functions as a good heat insulator. Normally the material with high specific heat capacity, okay, function as a good heat insulator, like a plastic, wood, and so on. Okay, next, cooking utensils. We have metal wok and clay pot. Okay, woks are made of metal with low specific heat capacity. Normally the body is made of material with low specific heat capacity. As such, food can be fried at high temperature in a short time because it can be heats up faster, so you can cook food faster. The handle is normally made of plastic or wood with higher specific heat capacity, so you can hold it during cooking. It does not become hot easily during cooking because higher specific heat capacity heats up slower. Okay, look at the clay pot. Clay pot, on the other hand, are made of clay which has high specific heat capacity. As such, food can stay hot for a long period, cools down slower. The used clay pot normally is a slow cooking process. It cooks slowly, but once it is cooked, it cools down also slower. So you can store food hot for a longer period. Okay, so we have a tips here. Okay, material with smaller C, smaller specific heat capacity, heats up and cools down faster. Okay, material with larger C, heats up and cools down slower. Okay, another application here, we have car radiator system. So burning of fuel in the car engines produces large amount of heat. This heat needs to be released to avoid overheating the engine. So how to cool down the engine? So we use water because water has high specific heat capacity. So used as cooling agent. A pump will pump water into the engine block. Water will flow through the engine block to absorb heat produced. Hot water flows to the radiator. Cool air is sucked in by fans so that heat in the hot water can be released quickly through cooling fins. So the water used due to its high specific heat capacity. Okay, outer layer of the space capsule. Space capsule on its journey back to Earth encounters air resistance when entering the atmosphere. This friction increases the temperature and causes the space capsule to burn. Therefore, the outer layer of the space capsule is made of substance with high specific heat capacity and high melting point. So sometimes the satellite or any space debris suddenly drop into the atmosphere of the Earth, so it will experience very high air resistance. So this one will cause heat energy to be produced at large amount. So that's why the material outside the space capsule is made of substance with high specific heat capacity and melting point. Okay, to prevent it from burn. Okay, production of lattice material and the construction of green buildings. What is green buildings? Not the green color buildings. So green building is the building that apply the smart energy use. They can save energy. They can prevent energy to be lost. Okay, so meaning efficiency in energy usage. Okay, the diamond building energy commission is built with an insulating concrete roof. That is the roof fitted with insulators using styrofoam boards. Styrofoam has a high specific heat capacity and can reduce absorption of heat from surrounding to reduce temperature inside the building. So means kept the surrounding in the building is not so hot. It's a bit not in a hot surrounding. So then they can reduce the usage of aircon, for example, or fan. Thus they can reduce the energy to be just lost like that. Okay, so you can discuss more, or you can find more information on this green building. Okay, now the application is a sea breeze during daytime. Okay, now we discuss what exactly happened at the beach. You can see this as sea and land. So land has lower specific heat capacity than the sea. Therefore, temperature on land rises more quickly than temperature in the sea during daytime. The air on land becomes hot and rises upwards. Cool air from the sea moves towards the land as sea breeze. Okay, so cool air from the sea move towards land, we call it sea breeze. So this one occurs during daytime. So we use the concept of specific heat capacity to explain this situation. Second one is the land breeze. This one occurs at night time, so it's cooling hour. So sea has higher specific heat capacity than land, so temperature in the sea drops slowly than the temperature on land. Meaning the sea water is warmer at night, but the land is only cold. Hot air above the sea rises upwards, cold air above the land moves towards the sea, so we call it land breeze. So from the sea to land, we call it, from the land to sea, we call it land breeze. This one occurs during night time. Okay. Okay, now look at some of the problem solving. Because we have formula, of course, there will be calculation problem. Example 1, 0.5 kg metal block heated by 50 watt electric heater for 90 seconds. The temperature of the block rises from 20 degrees Celsius to 45 degrees Celsius. Calculate the specific heat capacity of metal. Okay, you list down all the information. So the temperature change or temperature rise, delta theta, 45 minus 20, 25 degrees Celsius. Mass of the block, 0.5 kilogram. Power of heater, 50 watt. Heating time, 90 seconds. Okay, formula that we need to use here. Specific heat capacity equivalent to Q divided by M delta theta. So Q here is PT, PT. So use SI unit here. Power is watt, time is second. Okay, if given in minute, you need to convert to second. So you calculate, you get 360 joule per kilogram per degree Celsius. So this is the specific heat capacity of the metal. Second example, 20 gram of boiling water at 100 degrees Celsius is poured into a glass containing 200 gram of water at 28 degrees Celsius. Calculate the final temperature of the mixture water. So we have hot water and cold water. So the hot one will release heat. The cold one will absorb heat. So the mixture finally achieve one final temperature. Meaning temperature suddenly become constant, no longer increase. So that one we call it final temperature or temperature at thermal equilibrium. So we mark as Y. Let Y equals final temperature of mixture. So for boiling water, we put as M1, the mass change to kilogram, 0.02 kg. Temperature change, delta theta 1. This is hot object. When release heat, its temperature drop. Meaning the value of Y is smaller than 100. Thus, 100 minus Y. So change in temperature for delta theta 1. For water at 28 degrees Celsius, this one will absorb heat. When absorb heat, its temperature will increase, become Y. So the change in temperature, delta theta 2 equals to Y minus 28. So you must write correctly. If this one you write wrongly, so your answer also will be wrong. Okay, so assumption that need to be made in order to solve this problem is no heat is lost to surrounding. Meaning heat released by 20 gram of water is equals to heat absorbed by 200 gram of water. Then we can write Q1 equals to Q2. Q1 if M1 C1 delta theta 1, Q2 M2 C2 delta theta 2. Now the C is same because we are using the same material water. So C, then the C can be cancelled actually, both sides. So you substitute all the values, so solve it mathematically, so you get Y equivalent to 34.55 degrees Celsius. Therefore, the final temperature of mixture is 34.55 degrees Celsius. So for all calculation problems, one assumption that we made is no heat is lost to surrounding. Okay, so at the end of this topic 4.2, there is one project that can be carried out. We can make it as a project-based learning PBL. This is about the cluster homes. So cluster homes are homes which resemble terrace houses. However, three walls of the house are shared with the houses behind and beside it. You can look at here. Photograph 4.2 shows example of cluster home which has only one door for exit and entrance, while windows are only in the front part of the home. The shape of the home can minimize the use of land. However, when our country experienced the El Nino phenomenon with extreme rise in temperature, residents of terrace cluster home experience extreme heat. So it's very hot to stay in this type of house. So what you do, based on the above information, analyze the situation by listing the fact that problems related to the condition of extreme temperature in cluster home. So you try to identify what are the problems about the structure of the house and try to figure out, okay, any idea or solution to solve the problems. Okay, so what you do, you can sketch a model based on your solution. So this will become one of the project-based learning. Okay, so that's all for this topic. So you can go and read more on this information and do more exercise, especially a problem solving or calculation problems. Okay, that's all. Do subscribe, like, and tag for more oncoming videos. Support Physics Teacher.